Okay, so let's get going. So in the story, the boy cried wolf, the townspeople came, not realizing it was a trick. We're gonna create some hypotheses here. So we're gonna turn this into some statistical language. We have a null hypothesis. It says that there is no wolf. So this represents no change. There was no wolf before, there's still no wolf. The null hypothesis is that there's no wolf. The alternative hypothesis is that there is a wolf, and this is a change in the situation. Okay, so when the town people came running, what they did was they rejected the null. They rejected the idea that there is no wolf, and they decided that there is a wolf. And there was some pretty convincing evidence to do so. They heard someone crying that there was a wolf coming. So this is an example of a type 1 error, also called a false positive. So the townspeople rejected the null hypothesis when they should not have. So let's just make sure that's really clear. A type 1 error. They rejected the null, that there wasn't a wolf. They rejected that, but really they should not have rejected the null. Okay, so here's your handy mnemonic. This happened first. They rejected the null, and then they shouldn't have, so that is a type 1 error. That was the first event that happened in your story. It's hard to keep your type 1 and type 2 errors straight, so I hope this is helpful for you to remember that. Okay. So, of course, what happened later? There really was a wolf, but the townspeople didn't come. We still have the same hypotheses. So the null is that there's no wolf. The alternative is that there is a wolf. So what the people did here is they failed to reject the null hypothesis because they didn't find convincing evidence to do so. And now this is an example of a type 2 error, when you fail to reject the null, but you should have. And so your handy mnemonic here. This event happened second in the story, so it's a type 2 error. Okay. You will drive yourself insane trying to remember type 1 and type 2, or at least I will. I find that I have to always go through and kind of think through, wait, so I rejected the null, therefore that is a type 1. You know, I kind of have to verbalize it in my head in order to figure out which one it is. It might be something that clicks a little faster for you guys, but this, I think, is one of the more difficult concepts to keep straight, even though on its surface it's not that difficult of an idea. So here we go. You'll see you'll see two-way tables that look like this, and you'll see right here. So on the left we have whether the null is objectively true or if the alternative is true. And now we can't always know this, but let's just figure out what can happen. Let's say that we know that the null is true and we fail to reject the null. Well, that's a good thing. We don't want to reject the null if it's true. But if we do reject it when it's true, that's a type 1 error. If we have the alternative is true and we reject the null, that's a good thing. We want to get rid of the null if the alternative is actually true. But if we fail to reject the null when we should have, that's where our type 2 comes in. So, just different ways of visualizing this idea. All right, and we can, of course, substitute our own hypotheses into this. So we fail to reject that there isn't a wolf. In other words, we accept that there is a wolf and we run, but there really isn't one. You get it. Or rather, I don't know, I said that wrong, but I think you know what it was supposed to be. See, it's just weird stuff going on. So the false positive and false negative language will come into play. Type 1 is false positive, false 2 is false negative. And what we mean is when we say it's false negative, we are rejecting we don't reject the null. So we are negatively reacting to the evidence. We are not going to reject the null. It's negative, but really we should have. Okay. So probabilistically, here's how we would say this. The probability of a type 1 error, which is right here, is the probability of rejecting the null on the condition that it's actually true. So we want to think of this as conditional probability. And likewise, the type 2 error would be the probability of failing to reject the null given that the alternative hypothesis is true. Okay, so this is not, let me just say it this way. This is something that conceptually you'll need to understand. I'm not sure that this will come into play where you have to calculate probabilities this way, because we have other ways of finding our type 1 error. The probability of it and the probability of a type 2 error. Okay, so let's see, what are we doing with this one? There we go. This is what we're talking about now. What is the probability of a type 1 error? If you already read chapter 21, I encourage you guys to read that. You might already know. So we're going to logic through it just a little bit today. And I'm going to throw out a few facts, and I want you guys to figure out what you think the probability of a type 1 error is. We have a significance level of 0.05. All right, that's fact number one. We rejected the null because our p-value ended up less than 0.05. That's the other thing. The sample proportion or means, it doesn't matter what, so let's say it's a sample proportion, came from a random sample of the population. And with those three facts in mind, what is the probability of a random sample resulting in a p-value that would have us reject the null, assuming that the null is true? I'll put this in probabilistic language real quick. The probability of rejecting the null hypothesis on the condition that the null hypothesis is true.
Yeah, baby.
You pronounced it wrong.
All right. Any thoughts on this besides what's been shared? Okay, I want to kind of, before I show you the answer, I want to make sure this is really clear. We have, hopefully what I'm about to say makes it clearer. We have a sampling distribution that we're creating on the assumption that the null is true. So the null hypothesis, I'll just put whatever. The null hypothesis, the proportion of our null is going to be right there. So just randomly sampling, I could get a bunch of people from the population. This isn't the population, but I just get a bunch of samples and I end up with a p hat that lives right there. Now we might say, okay, that's not statistically significant. That can just be a random thing that could happen. I get another sample. Oh, it ends up right here. Here's my next p hat. This is p hat sub 2. Okay, still nothing really unusual. The next one happens to be right here, right just about at the true mean. That's our third one. Still nothing really unusual. And then the fourth one comes over here. All right, just with the random selection of people we got one that happened to be less than our critical value or our significance level. So this one we say is statistically significant. How likely is that to happen if we have a significance level of 0.05? Okay. Let's just, I don't know what I'm saying right now. You want to see the answer? The answer is, it's just the significance level. So just randomly, and it's fair that you don't know it, okay? It's really obvious once you see it in the end, and we'll talk about it a little more, but it is not something that immediately jumps to mind. It's like, oh, that must be the probability. But after we talk about it a little bit more, you'll say, oh, well, yeah, hopefully you say that makes sense. So if our significance level is 0.05, just randomly selecting from the population, we will get a statistically significant result 5% of the time, assuming the null hypothesis is true. And what we're saying is that, oh, that's statistically significant. So it gives us some evidence that really this isn't true, this null hypothesis. But it's still going to happen about 5% of the time just by random chance. All right. So I don't know if that's making 100% sense yet. So anyways, just the takeaway for right now, and I am going to show you a comic in a second that's going to help make this hopefully a little clearer. So the probability of a type 1 error is just your significance level. It's that easy. So if you want to change the probability of a type 1 error, all you have to do is raise or lower your significance level. So if you want to reduce the probability of this, what would you do to your significance level? So at an alpha level of 0.05, you have a 1 in 20 chance of a type 1 error. I don't want a 1 in 20 chance of that happening. So what should I do? I want it to be less.
Would you use 0.01?
Exactly. You want to drop that. So if I change this to a 0.01, now there's only a 1 in 100 chance of a type 1 error. And that's really good. So, and maybe we're satisfied at that level. Maybe we're really, really, really wanting to find something significant. So we go to a 0.001. So there's only a 1 in 1,000 chance of a type 1 error. I will say that how you change your type 1 error affects your probability of a type 2 error. But we'll talk more about that another time. All right, so let's look at this comic to hopefully really help this idea sink in. This is not the full comic. This is just the setup, and then we're going to see a few more pages. Okay. So let's move ahead. Okay, and the next page. Okay. So, final part. All right. Now, I'm not expecting you guys are sitting there just busting up laughing at this comic. It is funny in its own way. I want you guys to try and explain what the joke of this comic is. And I'll just run through the comic one more time while you guys are thinking about that. Okay, so maybe not necessarily explain the joke, but explain like what is the point that this comic is making? Okay. We are going to have more discussion in class today, so hopefully you guys feel a little better about jumping in later. But let me ask this question. How many colors did they investigate?
Twenty.
20.
20. They investigated 20 colors. How many did they find a link with?
1.
And at a significance level of 0.05, how many would you expect?
1 per 20.
You would expect 1 in 20. If we think about this in terms of binomial real quick, we can remember that the expected value for a binomial is going to be n times p. So if just by random chance you have a 1 in 20 chance of this happening, and you're testing 20 different colors, then just by random chance you're going to get one statistically significant result. Does this actually mean that green jelly beans are linked to acne in reality? I would guess.
No.
Okay, no. I would guess that there's really not a link, but this is kind of the shotgun approach to research. You just test a bunch of things until you find something that's statistically significant. And that's the danger of this. So we're going to talk a little bit. Now, it's important to know the difference between type 1 and type 2 errors, and the probability equals the significance level for type 1, all that fun stuff. But now we're going to talk a little bit about the idea of p-values and this inference, these inference tests and hypothesis testing in general. So there's a lot of criticisms of the stuff that we're learning in the academic world. And I'm assuming that at least one of you will go on to college where you'll have to do some research where you're going to have to deal with statistically significant results. So this is not speaking so much to right now in this class, but as you move forward, this is a takeaway you can take from this class. Some people argue that only smaller p-values should be considered statistically significant. And a lot of people will say that 0.05 is still too high of a p-value for it to be statistically significant. So they're saying 0.01 maybe should be the standard. Here's other ideas. So there's such a thing as, and I'll just bring up the next part, p-hacking. And I don't know if you've ever heard that term, but p-hacking is where you collect a bunch of data, you just kind of throw it into a statistical blender, and you figure out what comes out. And then from there, you revise your hypothesis, your significance level. You maybe can even throw out some of the data that you decide after the fact wasn't very good. And you can just kind of massage the data. You can really, in some cases, be unethical about it. And you can come up with a statistically significant result that doesn't really map onto reality. It's not a true result. You just did some p-hacking. I should say researchers. So requiring hypotheses and significance levels to be announced before conducting the research, before collecting any data, is very important. And announcing exactly what your methodology is going to be. You don't want to change it in the middle and say, oh, well, if this data was collected in this particular way, then I'm going to throw it out because it's biased. You can't decide that afterwards. You have to decide it at the beginning. So this is going to prevent p-hacking, and you're only going to get there's less user intervention at that point. Now, some journals also require duplicating the research, called replication studies, to make sure that the result is statistically significant a second time. So what has been found is that a lot of statistically significant findings cannot be replicated and have been thrown out. And so for many years, we thought there was a link between this and that. But then it was later researched, restudied, and they couldn't find that same link a second time. They're like, oh, well, let's just throw this out. And that's when you've probably seen all kinds of articles that say, oh, you should drink coffee in the morning because it's good for your health. Oh, coffee is actually terrible for your health. It goes back and forth, right? And what happens is, it's not necessarily the scientists who do this, but it can sometimes just be the media blowing things out of proportion. But anyways, what they're finding is a statistically significant result, right, that maybe was just due to random chance, okay? And so you have to get a lot of evidence before you can really make a definitive decision. So again, that's something that I hope you can kind of take away, the way that p-values can be misused. And so here is some important stuff. Make sure you're objectively analyzing your data by establishing methodologies and rigorous criteria before you collect the data. Very important. It can still result in mistakes, but it's not likely to happen as often, and your professional reputation is on the line. Now, that's a bit extreme to say that, but also in some ways not. You want to make sure that you are just approaching things in an objective way. Certainly, you want to make sure that if a mistake was made, it wasn't because you acted unethically. You can just later say, well, I guess it was random chance. But think of this, if you had to do research and you collected data on a certain number of students at your college, and then you ran your z-test for proportions, and you found out you had a statistically significant result, whatever this question happened to be of interest. But then maybe a good second step after that, and you decide this at the beginning of your research, you say, you know what, I got a statistically significant result, and what I'm going to do is I'm going to go and get a new random sample, and I'm going to run the test a second time. Because if it was just a random chance that you picked a certain group of people that gave you a statistically significant result, then the second time you do it, you shouldn't get that happen again. There's only a 1 in 400 chance that you're going to get a statistically significant result twice if it's not statistically significant. I'm saying statistically significant so much, I hope it still means something to you. Okay, so running the same test twice, collecting 2 samples and testing them independently is a good way of verifying that you have a real result on your hand. Okay, so how are we feeling at this point? You feel like you understand the type 1 and type 2 errors and a little bit more about it? Okay, got some thumbs up. So if there are still questions coming up, that's fine. You can stick around, we can do that. So now, type 2 errors. This is another discussion question. I'm going to try and not speak as much on this one. Now, type 1 error is sometimes considered worse in the academic world because it kind of shows that you weren't as rigorous in your research, like we were just talking about. You rejected the null when you should not have, and maybe you should have had better methodologies and replicated your studies. But type 2 errors might be worse depending on the situation. Failing to reject the null when you should have. So we're going to look at a scenario here. I made this up, but let's just go through this. You're researching if a particular chemical common in many foods is a carcinogen, specifically for colon cancer. Trying to be rigorous in your research, you're only going to accept results significant at the 0.01 level. When you compare the sample proportion of those who have colon cancer after ingesting large amounts of this chemical to the proportion of people in the population with colon cancer, you end up with a p-value of 0.0101. In this case, do you fail to reject the null hypothesis?
I'd say maybe no, because maybe there could be some variability in the p-value that would drop it below 0.01 or like bring it a little bit above of it. I don't know.
Okay, no, I hear you. So, right, and I think kind of what I'm hearing is like, we're right at that boundary, and you almost want this to be a very black and white decision, but it's almost in this gray area. This is so close. Do I really reject this? And I think to fully answer this question, let's go through and remember, we're about to go to a blank page. So remember this scenario, okay? So we are doing a study and we got 0.0101. Okay, so let's consider what a type 1 error is. So in this study, what would a type 1 error be? I'll go ahead and provide the hypotheses for you. So the null hypothesis is that the chemical doesn't cause cancer. The alternative is that the chemical does. Now, of course, we wouldn't phrase it like this. We would be talking about the proportions being equal versus the proportions are different. But we're basically saying it doesn't cause cancer or it does cause cancer. And again, just to hedge my bets a little bit, we have evidence that it causes cancer. We're not looking into the actual biology of it. So type 1, first of all, just in general, what does type 1 mean? Does that mean that we reject the null and we shouldn't, or that we fail to reject the null and we shouldn't?
We reject the null, but it's
Okay.
true.
Yeah, there we go. We reject a null that's true. So a type 1 error, what are the consequences? What is it in this case? When we reject the null, but we shouldn't, what are we essentially saying for this scenario?
We're saying that it does cause cancer, but it really doesn't.
Perfect. And I'll put it in a little better terms right here compared to how I phrased it before. I'll say the chemical, okay, actually, let me rephrase this. We say the chemical is linked to cancer, but it's not. All right. You can't really read the end of that, but it's okay. But you hopefully remember. So if we make this mistake, what are the consequences? We go and we announce to the world, this chemical is linked with colon cancer. It's really not, but that's what we tell the world. What are the consequences?
People unnecessarily link that to colon cancer and might avoid it.
Okay. So food avoided unnecessarily. What else? It's not the only consequence.
People are gonna think that they're not gonna get cancer because they're not getting the chemical.
There you go. Perfect. So there's misinformation. I like that one. Well, I like how you were thinking through that. Misinformation, thinking you're safe when you're not. Okay. I'll throw out one real quick that came up in 5th hour. What about the people that manufacture these foods, whatever the word is, produce these foods? You know, you're opening yourself up to some legal liability, right? They're opened up to liability because people can sue them for producing cancer-causing chemicals, even though it really doesn't. So I'll just put legal liability. And you'd like to think that you as a researcher, you're immune from liability, but you know, you're a target at that point because you just announced to the whole world that this chemical that's commonly produced causes cancer. And all these companies that were making money off of this, they're not going to just roll over and be happy with that. So anyways, there are one other consequence that came up was that, you know, if people avoid certain foods, they could be missing out on certain nutrients also. Maybe they don't replace it with healthier options. So maybe health consequences from eating different foods. And who knows, maybe they accidentally turn to another chemical that really does cause cancer. All right, so you can see some of these are hypothetical, all of these are hypothetical, but some of them maybe are more or less likely consequences. All right, so the type 2 error. We have failed to reject the null when we should have. So now in this scenario, what does that look like?
It is a carcinogen, but we didn't announce that.
There you go. So we say it is not linked to cancer, but it is. So remember, this is all very situation dependent. Sometimes a type 1 error, or type 2 error can be worse. Let's go through the consequences. So let's say we say it's not linked to cancer, but it really is. What's a consequence here?
People are gonna get cancer.
There you go. I'll just put cancer. Any other consequences? We don't have to spend all, 10 more minutes on this, but any other consequences that could result here?
We could get like liability
There you
stuff
go.
too.
There's legal liability in this one also. So maybe this one's a wash as far as it goes, because no matter what we announce to the world, there could be some legal liability. Okay, and I'm sure we could come up with others, but on balance, when you look at these two outcomes, a type 1 error versus a type 2, which one seems worse to you?
The type 2, because it causes harm.
Okay. And of course, you can all decide individually for yourself which one's worse, type 1 or type 2 error in this scenario. But let's say that we go along with what Cyan just threw out there, and that type 2 is worse here. In this case, maybe going back to that, we ended up with a 0.0101. Now, we don't want to do any p hacking necessarily. We don't want to just change our significance level so that we can report that. But we could still kind of announce that and say in our own way. It was not statistically significant, but it is a meaningful difference. And this points to a possibility that there's a link between this chemical and cancer. Okay, so you can somehow try and reject the null in your own special way. Okay, I mean, you run into that do we want to be incredibly rigorous scientists and we set our rules out and we are not going to break them because we are working with that level only, or are we trying to avoid the worst error? I think type 2 would be a worse error here, so we're going to go ahead and reject the null. Okay, so the last little bit, and I hope you're actually kind of trying to process through that one and it was making sense. If you have questions about it, you can stick around. So the probability of a type 2 error, you guys might be wondering. That's what we're going to talk about on Tuesday. We're not going to do that today. So we're going to run through two little practice problems. Hopefully it doesn't take us too long if you guys are chipping in. So let's go through this real quick. The manager of a fast food restaurant wants to reduce the proportion of drive-through customers who have to wait longer than 2 minutes to receive their food after placing an order. Based on store records, the proportion of customers who had to wait longer than 2 minutes was 63.63. To reduce this proportion, the manager assigns an additional employee to drive-through orders. During the next month, the manager collects a random sample of 250 drive-through times and finds that p hat is 0.576. The manager then performs a test of the following hypotheses at the significance level of 0.10, where p is the true proportion of drive-through customers who have to wait longer than 2 minutes to receive their food. So we want to describe a type 1 and type 2 error in this setting. All right, we have our hypotheses. Remember, type 1 is we reject the null, but we should not have. So what does that mean in this scenario?
He said that the proportion of people that had to wait less than 2 minutes was less than it actually was.
Okay, so we rejected the null when we should not have. And so we're saying that this extra person on drive-through helped when really they didn't. And the proportion is really the same. So of course, we could find out if this is a type 1 error if we did another sample of 250 and we got like 0.64. And so it didn't really change that significantly. So anyways, yeah, this is a, so we could phrase it different ways, but let's just say that we conclude that the extra worker helped, but they really didn't. Okay, so, well, I could maybe add in here, we conclude. Okay, so we conclude that that extra worker helped out when really they didn't. All right, now the type 2 error. What would a type 2 error look like in this scenario?
Would it be that the extra person did help?
Yeah, in reality, they did help, but we conclude what?
Oh, that it brings the times down?
So what we're saying, when we fail to reject the null and we should have, what we're saying is that, oh, that worker didn't help us at all. So we conclude that the worker didn't help. But they really did. Okay, so between these two, it's certainly, we're not talking about cancer anymore, but between these two, which one's a more serious error? So I hope you can see with this type 1 and type 2 error and all this, this is where statistics gets a little bit more gray and maybe a little less just intuitive, where you really have to think through the scenario. If we focus on the consequences here, just because I want to move this along a little bit, type 1, the biggest consequence here is that we say the extra worker helped when really they didn't help. And the biggest consequence here is that we're paying an extra worker. All right. So extra payments, extra worker payment. All right, so that's the biggest consequence right there, I would say. Type 2, we conclude that the worker didn't help, but really they did. And the biggest consequence here is that more people have to wait longer. Or I'll just say wait more than 2 minutes. Okay, so which is more serious? That you're paying an extra worker, or that a higher proportion of people have to wait more than 2 minutes?
I think type 2 is worse because, I mean, even if they're paying that extra worker, the consequences of type 2 could be like customer complaints, and then they could lose sales, and then overall they'd have like a net loss because they didn't use that worker that was actually really helpful. Whereas if they weren't helpful, they would just be losing some money by paying for that extra worker instead of a lot from type 2.
Perfect. Yeah, I think that's excellent analysis of it. And this is not something that you're going to be expected to do, but we could go through and we could actually create, kind of the expected payout for all 4 scenarios. That this is really true, and we correctly reject the null, all this stuff, and we could go through and we could figure out how much, if I can write, how much money we're out, or, you know, if it maybe there's a negative dollar amount here and we get a positive dollar amount here, and then something like that. So we could go through and we could figure out and turn it into economic terms. We're not doing that. We're worried about that right now, but it is something we could do statistically. And what you just said, I think, speaks right to that. They calculate and figure out how much their net loss is going to be in any scenario. And there's a lot of that in what's called game theory. So if you like this stuff, game theory is really what we're talking about. Okay, so based on question 2, do you agree with the company's choice of a significance level of 0.10? So just to make sure this is helpful, the probability of a type 1 error is going to equal the significance level. So if I decide that a type 2 error is worse than a type 1, we should add right here that type 1 and type 2 are inversely proportional. Sometimes you use that symbol for inverse proportionality. All right, so as type 1 error probability goes up, then type 2 error goes down. Now, we haven't talked about that explicitly, but I just want to mention that now. So do we want a higher type 1 or a lower? Or do we want a higher significance level or a lower significance level?
Higher?
Higher. I know this requires like 3 steps of abstraction for us to kind of work through this. We want as low of a type 2 error as possible because we've decided that that's no good. So in order to do this, we want to increase our type 1 error, our probability of that. And in order to do that, we need to raise or have a high significance level. We don't want to make it too high because then that could just be ridiculous. But 1 in 10 chance, would you conclude that that's a pretty fair significance level? It should be raised or lowered or what? Let me ask this question, because maybe you're not sure if 1 in 10 is the right level or not. So I'll just simplify your choice. Should we lower the significance level to 0.05?
No.
No, we should not. So if we lowered the significance level to 0.05, then we are increasing our type 2 error probability, and we don't want that. So bottom line, I think it's fair to say this is a good significance level choice. I don't think we want to change that to 0.2. That seems a bit crazy. So anyways, hopefully you're able to follow through the logic on that. Okay, the last little bit, the p-value of the manager's test is 0.0385. Interpret the p-value. So here's how we would interpret this. I'm just going to run through this part. There is a 0.0385 probability of getting the results we did or more extreme. Assuming the null hypothesis is true. Okay, and that's really what the p-value, almost the definition of a p-value. So there you go. So if we have only a 4% chance of getting the results we did, assuming the null hypothesis is true, this is what we would call a statistically significant result. We would reject the null hypothesis. We would not end up with a type 2 error. You only get that if you fail to reject. So there we go. Hopefully this was helpful, kind of thinking through it a little bit. And you might not like this content right here. This might be exactly the kind of stuff that drives you crazy. And for me, it's definitely the kind I have to stop and think about this more than any other type of question. So it's not simple stuff, but that's about all we're going to be doing today. I wanted to look at one other problem here. And the one thing that I'm going to skip part of this, we are not talking about the power of the test today. We'll do that on Tuesday. So this one is pretty tricky. And I'll just offer up at the beginning, I didn't know how to do this one in 5th hour. I had to look up the answer in the back of the book. So let's see if I can walk you through this. So we're testing for Alzheimer's disease that, and testing there, can be a long and expensive process consisting of a lengthy test and medical diagnosis. Recently, a group of researchers devised a 7-minute test to serve as a quick screen for disease for use in the general population of senior citizens. A patient who tested positive would then go through the more expensive battery of tests and medical diagnosis. The authors reported a false positive rate of 4% and false negative rate of 8%. I'll tell you, for our questions right here, we don't need to know this. All right, that's going to matter when we get down to finding the power of the test, but for right now, it doesn't matter. So we want to come up with our hypotheses, H sub naught and alternate. And just to help you out, because this is where I was getting confused, where I was like, are we looking at proportions in the population being greater than or equal or less than a certain amount? But no, here's the hypotheses we're testing. Not specifically, but generally we're saying when a patient comes in, for that specific patient, what is the null hypothesis going to be? What is the no change scenario for a patient after they take the 7-minute test?
Is it if they have a negative result?
A negative, okay, yeah, and that's essentially right, yeah. So if you came in and before you took this test, the assumption is you don't have Alzheimer's. After you take the test, the null hypothesis is that you don't have Alzheimer's. You know, it's unlikely that you have Alzheimer's. So no change is that, yeah, you still don't have, you get a negative result on the test. So the null hypothesis is that I'll just say no Alzheimer's. So what would the alternative hypothesis be?
You have Alzheimer's.
Yeah, there you go. You have Alzheimer's disease. So, all right. So it's tricky coming up with these hypotheses. So we're only talking about an individual patient has the null hypothesis and the alternative hypothesis individually, and we're going to kind of settle that. So type 1. What would that be in this scenario? A type 1 error.
Saying they have Alzheimer's, but they don't have it.
Okay. Saying that someone has Alzheimer's, but they don't. Okay. And a type 2 would be?
Saying they don't have it and they do.
Exactly. Saying they don't have Alzheimer's, but they do. Now, I'm not going to make us list out the consequences of a type 1 or type 2. I want you to kind of individually think through it. And which one do you think is worse in this scenario, a type 1 or type 2 error?
Type 2.
Type 2.
Okay, I'm hearing type 2. And we can kind of answer the last question. So let's just say maybe you agree it's type 2. And if you think type 1 is worse, that can be an opinion. So this is not one of the questions asked here, but just to say this, if type 2 is worse, our significance level, do we want it to be a 0.05 significance level or a 0.01, assuming type 2 is worse? But you can circle whichever one you think we should pick. Okay. 0.05. Does anyone disagree with that? I don't. Okay. I think that's what I would pick too. So remember, a higher significance level right there means a higher chance for type 1 error, which means a lower chance for type 2. So if type 2 is worse, we want to reduce the probability of a type 2 error. We pick the bigger significance level. And just to figure out what this 0.05 is, this is kind of where part of this is it's a nice balance between type 1 and type 2 errors, which is why this is a nice one to land on. Though again, maybe we, depending on the scenario, the 0.01 is better. So that's about all we're going to talk about today. I know it's not very much as far as amount of content, but the content that we went through is kind of tricky to wrap your head around. So here's what I want you guys to be working on tonight. We've got, of course, your homework, a number of problems, chapters 21 and 23. What we did today was from chapter 21, but not all of it. If you read that, you're going to be set up. 23 is dealing with means. So read up on that, skim through it so that you're a little bit prepared for Monday. And besides that, have a wonderful weekend. Enjoy your Halloween, and I will see you then. Monday, that is.